Hello, today we're going to do an introduction to waves, some wave properties, and continue on with what we've been learning so far. So let's get going. We've already done a lab with a pendulum where we looked at the period of the pendulum, which was the time required to make one complete swing. And we had a couple of definitions where this is the amplitude and this is the equilibrium position. And we're going to equate that to waves today and look at this a little bit more in depth. A wave is what I call a traveling energy disturbance. Waves travel through a medium or space and they transport energy without actually transporting the medium from one place to another. Medium is just a fancy word for a material. So for example, if I were to throw you a baseball across the room, I would be transferring the baseball, the mass, the material, and its kinetic energy from one place to another. Now a wave doesn't do that. A wave just transfers energy, all right, without actually transporting the medium from one place to another. A mechanical wave is a wave that we're going to look at first, and the mechanical waves are waves that require a medium to travel through. Sound is a mechanical wave. Sound needs something to travel through. It needs air for us to transport the energy from one place to another. Or sound waves can travel through a material. They can go through the wall of your house, but it's not quite as strong as if you're just standing next to somebody. It takes a lot more energy to pass it through your wall. All right. So a mechanical wave requires a medium. Next, not in your definitions, but important because we're going to do it next, is an electromagnetic wave. An electromagnetic wave transports energy but does not require a medium. A great example is light. Light can get to us from the sun. Light comes from the sun, hits the earth. All right. We see stars out in the sky, so light's getting to us from the stars, traveling millions and millions of miles. Well, light can also travel through a medium. So light can travel through glass. But it can't always travel through every medium because, for example, if the light doesn't travel through the roof of your house, right? Other electromagnetic waves travel through the roof of your house, but not necessarily light. For example, you can use your cell phone in your house. All right, because your cell phone is using electromagnetic waves. They're using what we call microwaves. Yes, the same microwaves in your microwave oven. All right, so we'll be working with electromagnetic waves a little bit later. So let's just concentrate on mechanical waves. So mechanical waves come in two flavors. So the first mechanical wave that we want to look at is what we call a transverse wave. A transverse wave is a wave that transfers energy by displacing the medium perpendicular to the direction of the wave motion. For example, if I take a slinky, stretch it out on the floor, have somebody else hang on to this end, I can shake it back and forth, and the medium is going to go up and down, but the wave is going to go down along the slinky, just like Paul Anderson did on the video, the intro video that he gave you. Or that I had you watch. So the wave's going to go travel this way, but the medium's going up and down. The slinky is not physically going from this end to the other, but its energy is. If you don't believe energy is being transferred by a wave, just stand in the ocean on a day when a big wave comes and hits you and knocks you over, or in the wave pool. There's definitely energy traveling through that wave. So that's a transverse wave. Our next flavor is what we call a longitudinal wave. These are often called compression waves as well. You'll hear that if you look at any geology and they talk about earthquakes. All right, they call them compression waves or pressure waves. And the reason for that is if I took that same slinky, stretched it out across the floor, and just pulsed it, pushed on it, push on it, push on it, push on it, I would have these little pulses that travel through the slinky. All right, here's one here, here's one there. All right, what they do is they compress the slinky, and so that's why we sometimes call them compression waves. So what do these waves do? These waves transfer energy by displacing the medium, in this case the slinky, in the direction of the wave motion. Good examples of compression waves or longitudinal waves are tsunamis, that do that. There's some earthquake waves that are compression waves. Sound is probably the most popular one for us. That's a compression wave. So we have transverse waves that displace their media back and forth, up and down, so to speak, as the wave moves that way. And we have longitudinal waves, which transport the energy this way, and the medium displaces back and forth this way in the same direction that the energy travels. So let's look at a couple of wave diagrams. So here's some terms that you should be familiar with when we talk about waves. This is what we call the crest. That's the top of the wave. This is what we call the trough. A trough is like a, oh gosh, it's hard for me to find an example for you. It's easy for me because the gutters on the side of our house or up at the roof, we call those eave troughs back in Michigan. It's kind of a weird name. And what it is, a trough is like a little channel like that holds water. If you ever see a movie where there's like animals eating in a long trough, you know, like at a cow farm or something like that. So that's what a trough is, a little depression like that. Wavelength, that's the length of the wave. So wavelength is from one point to an identical repeated point. From one point to an identical point somewhere else. So we could measure the wavelength from here. Let's see, we go down through the trough, up over a crest, and back. Okay, so that's one wavelength. We could go trough to trough. We could go crest to crest. I oftentimes like to measure wavelength if I'm trying to do a really good job at it, right where it crosses this point, because I can line that up with where it crosses this point real easily, and it's kind of hard to tell exactly where I am up there. All right, so what is this line? This line through here, well, if this were a water wave, this would be when the water's flat. So we had a name for that with the pendulum, and we called it the equilibrium position. So that would be this wave without no motion at all, no transfer of energy. So amplitude, right here, from there to there, is just the measurement of the maximum displacement from the equilibrium position. Do not make the amplitude from here down to there. That's a no-no. A lot of people do that, okay? That's twice the amplitude. The amplitude is from equilibrium all the way out to the maximum displacement. That's exactly what it was with our pendulum. It was how far we pulled the pendulum back. We measured it as an angle, all right, but that doesn't matter. It's still the maximum distance from the equilibrium. Okay, longitudinal waves. I don't have a diagram for this. I guess there's one up on the side with the notes. Basically, there's a couple parts of a longitudinal wave. I think the most important part of that is to know that the wavelength is from the center of this compression to the center of the next compression. So I just already got to one of the definitions. We call this a compression, and that a compression. We call this part in the middle, which would be the trough. This would be the crest to crest, hence the wavelength. This would be trough to trough, wavelength. All right. This little spot in this very center is called a rarefaction. A rarefaction is just a fancy science word meaning spread out. So if you're compressing, so think of the slinky. So the slinky's loose. All these loops are going to be equal distance from each other. So what do we have to do? To compress this, we have to spread out this a little. All right, so that's why we have these spread out regions in the longitudinal waves, because the matter cannot be created or destroyed. We didn't add loops to the slinky, all right, in order to make these compressions, so we have to stretch it out there. So those are called rarefactions. All right, so wavelength, from compression to compression, rarefactions between the compressions here. We generally write them or measure this from here to here because these are easier to identify than this maximum spread out area. Sometimes with waves, we actually plot the wave on a diagram as a transverse wave, but it's really a longitudinal wave because it's kind of hard to identify all of this stuff right here on what the wave physically looks like. So a great example of that is sound waves. If you ever do anything with video editing or sound editing, you will see sound waves drawn this way, all right, like on a computer screen if you're analyzing sound waves. But they're really they're really longitudinal waves like this. This is what they would physically look like in space, not space meaning outer space, space meaning like the air, all right? So this is what they would physically look like, and this is what we draw them as because it's a lot easier. You could also think of this as, I did mention that we call these waves often pressure waves, okay? So this would be high pressure, this would be high pressure, this would be equilibrium, and this would be like a negative pressure because it's spread out. So high pressure to negative pressure to high pressure. So lastly, we have a couple definitions. So we already know one of these, the period, because we work with that with the pendulum and the simple harmonic oscillator. So the period is the time for cycle. All right? It would be, in a wave, it would be the time for a whole wavelength because we looked at the pendulum. If we let go of the pendulum, the period would be the time for it to come all the way back to our hand. Well, that would be one complete wave. It would be like crest to crest. So what do we measure the period in? Seconds. The symbol is just a capital T. It stands for time. Frequency. Frequency has a symbol of the small f. It's usually like a script F, but when I'm typing stuff up, I just make it italics. But frequency is kind of like the word frequent. It's how often something happens, right? Like if you, like Striz these days, you know, I go to the refrigerator frequently, all right? 20 times a day, all right? What is that? That is cycles per time, not time per cycles. So how do we generally measure frequency? The standard is 1/seconds. All right, so if I have a frequency of 10, that would be 10 per every second. The name for that, 1/seconds, is called a hertz, and Hz is the symbol. So if I went to the refrigerator 10 times a second, I would be going to the refrigerator at 10 hertz, 10 times a second. Some of you that do music, you know some of these. If you've heard this phrase maybe before, like 256 hertz, that's the vibration that causes middle C on a piano. 440 hertz is the note A. Right? So we have some experience with this term already, possibly. And then since one of them is time per cycle and the other is cycle per time, it should be obvious that there's a relationship between the two. If we have frequency, we can easily find the period. They're inverse of each other. So the period, T, is 1/frequency, and likewise, the frequency is 1/period. So you only have to find one of them, and you take the inverse on your calculator, that's the x to the -1, and that will give you the other. Well, that's it for now. See you later.